And welcome back to Chapter 13 podcast. We are still in 13.2, the nature of liquids. Where we left off last time was a discussion about why liquids behave the way they do. We said that liquids, the particles like to stick together a little bit more than they do with gases, and so they're held a little bit more tightly together, actually a lot more tightly together, where they're still able to move around one another, but yet they are still in a condensed state, as opposed to gases that are not attracted to one another, and those particles can go anywhere in the container that they want. The last thing we talked about in that podcast was the situation with evaporation and vaporization. Vaporization is when particles have enough energy to overcome those intermolecular forces and they can break free into the gaseous phase. Generally that takes place as you heat something up and it starts to boil. Evaporation, on the other hand, is when the particles at the surface, some of them have enough energy already to overcome the intermolecular forces, and they just go into the gaseous phase on their own. Now that takes us to these two diagrams right here on your notes, where you have an open container and a closed container. Let me again switch my color. There we go. In our first situation, we're dealing with an open container, and in our second situation, we're dealing with a closed container. What happens in an open container as something vaporizes or as something evaporates, the particles, if you notice, are going into the gaseous phase. That's what these arrows are showing right here. They're overcoming the intermolecular forces, and they're going into the gaseous phase, and then some of these are coming out of the container. In the second situation, you have a closed container, so as they go into the vapor phase, they're bouncing off the walls, and eventually they crash back into the surface of the liquid. So you have a situation where you have eventually the same number of particles going into the vapor phase as you have crashing back into the liquid phase. At that point, you have a situation which is called equilibrium. And at this particular point, the pressure is not going to change. You're going to have the same number of particles in the vapor phase as you have in the liquid phase, or at least, you're going to have a certain number of particles in the vapor phase that's not changing. And so the pressure is not going to change. And at that point, you have established what is known as a vapor pressure. The vapor pressure of a liquid at a certain temperature is the pressure when you have that equilibrium situation where the number of particles in the gaseous phase are not changing. Now in an open container, you're not going to get that. Yes, occasionally some particles might crash back into the liquid phase, but you're never going to establish an equilibrium because particles are going to be leaving the container. And so there's always going to be more particles going into the gaseous phase than there are going back into the liquid phase. And eventually, as you know, if you've ever had a glass of water that sat out, eventually, over time, more particles are going to be leaving, and eventually all the liquid particles are going to be gone. They're going to be evaporated. But in a closed container, that's not the case. In a closed container, eventually the number of particles going into the gaseous phase equal those that crash back into the liquid phase, and you establish this equilibrium situation. So, scrolling down. Vapor pressure then. Vapor pressure is the force exerted by a gas above a liquid. And again, that's going to have to be in a closed container because the pressure in an open container is going to be continually leaving. Alright, so that's an important definition. Of course, going between a liquid and a gas is called evaporation or vaporization, and going back from the gaseous phase to the liquid phase is called condensation or condensing. Typically, if you force this to happen, this will be taking place in a process known as boiling. You already know that. And returning back to the vapor from the vapor phase to liquid is called condensing. Condensation is the actual material itself. The process is called condensing. Moving on. Table 13.1 shows different vapor pressures of various liquids. Notice what's happening. Let's take a look at water. As you go up in temperature, the vapor phases are going to increase. Now let's think about why that would be. Why is the vapor pressure of a liquid going to increase with temperature? Well, again, if you think about this in terms of a closed container, and particles will only, there's a stopper here. There we go. Here's our liquid. Here's our particles. We're just going to draw them far apart, but they are touching one another, very close to one another. And you have particles going into the vapor phase, and you have some of these particles going back into the liquid phase. Okay. What's going to happen at a warmer temperature? You're going to have more particles that have enough energy to overcome the intermolecular forces. So you're going to populate this space above the liquid with more gaseous particles. With more particles in the vapor phase, they're going to be crashing into the sides more, and that's going to increase the pressure. If you increase the temperature even more particles will have enough energy to go into the gaseous phase, and so more particles will be crashing onto the walls, increasing the pressure, and so on and so forth. So the higher the temperature that you have, the more particles that you're going to have in the gaseous phase, and the more collisions you're going to have on the walls of the container, so you're going to have greater pressure. So that explains why as you increase temperature from 0 to 20 to 40 to 60 to 80 to 100, you're getting an increase in pressure because more particles will be in the gaseous phase. Now, what about the fact that different liquids have different vapor pressures at the same temperature? Well, again, it goes back to the amount of sticking that the particles have with one another. Those what we call intermolecular forces. We've mentioned that a lot. Intermolecular forces. Some people will abbreviate them IMFs. The more the particles stick together, the more they tend to stay in the liquid phase, and the fewer of them would be in the gaseous phase. Water loves to stick together. So at 0 degrees Celsius, it has a fairly low vapor pressure. Diethyl ether, whatever that is, you have to know what it is. Diethyl ether does not stick to one another. So it's very easy for these things to go into the vapor phase. Here's our little container. Here's our liquid. If this is diethyl ether, none of these particles want to stick together. So it's very easy for them to get into the vapor phase. A couple of them will stick together, but they're going to be going to the gaseous phase a lot. So at 0 degrees Celsius, you're going to see a ton of gaseous particles because nothing is holding them down in the liquid phase. Ethanol is somewhere in the middle. It's much more like water, but ethanol sticks together a lot more. So more of them would stay in the liquid phase stuck together. Fewer of them can overcome those forces to get into the gaseous phase. So vapor pressure is a function of how much they stick together, the amount of intermolecular forces. The more they stick together, the more they stay in the liquid phase, and the less vapor pressure they have. The less they stick together, the more of them that can escape into the gaseous phase, and the higher the vapor pressures. In the next podcast, we'll wrap up this section, and we're going to talk about what that means in terms of boiling. Okay? We'll see you next time.